Hi everyone, this is Kalyan Kumar and welcome to my channel Chemistry Tutorials and welcome to another video on solid state. Today we are dealing with part 7 of the 10-part series of solid state and today it's the turn of voids. In the last video of part 6 we talked about hexagonal primitive unit cell, its packing fraction, its coordination number, and right now we're going to talk about voids. So in this section we talk about voids, and basically voids are of two types. Generally we talk about two types of voids, and they are octahedral voids and tetrahedral voids. And these voids are only found in face-centered cubic and hexagonal primitive unit cells. That is the CCP arrangement, cubic close packing, and hexagonal close packing arrangement. So first of all we're going to look at both these voids in FCC unit cell. So let's start with octahedral void in FCC. Now I'm going to draw only certain atom of FCC. There are going to be two types of atoms, blue and red. Blue are the ones which are forming the FCC and red is the one which will be inside a void. So I'm going to draw this corner, face center, back face center, and I'm going to place a red atom at the center of the edge. Now if you notice, this edge length is a by 2. Now assume that this is big enough to be in contact with this. Then it will also be in contact with this because this is also at a by 2. This is also at a by 2. This is also at a by 2. And the next unit cell has a back face which is also at a by 2. The unit cell at the back of this has a left face which is also at a distance of a by 2 from this, and there will be no other atom at a distance of a by 2 and no other atom at a distance less than a by 2, and therefore this atom is going to coordinate with these 6 atoms and they are in the form of an octahedron. This is a square and these are the 2 atoms on top and bottom of the octahedron. Now this atom is present at the center of edge. So similarly there would be 12 edges. There are 12 edges in a cube. So in each edge center you're going to find an octahedral void. In case this atom is not there, we call this space as void. So there are going to be 12 of them, and each octahedral void which is present at the center of the edge is being shared by 4 cubes. One is this, the other is this, the other is this, and the one here. So 4 will share. So the contribution of this void for one unit cell is going to be 1 by 4. And there are 12 edges. So 12 into 1 by 4 makes it 3. So one octahedral void is found at the center of every edge of the unit cell. There are 12 edges in a cube. Each edge is shared by 4 unit cells. Effective octahedral voids from edge centers would be 3. But there is one more. This is the octahedron I was talking about. Now, let's take the cube. Now let's place the red at the center of the cube. Then it will find 6 face-centered atoms at a distance of a by 2. The right face center, left, back, front, top, bottom, all at a distance of a by 2. That means this is also an octahedral void, and since this is right at the center of the cube, its complete sharing is going to be 1. So there is one octahedral void at the center of the unit cell which has a 100% contribution to the unit cell. So the total effective number of octahedral voids is 4. And it has been found that the number of octahedral voids is always equal to the rank of the unit cell. And of course later on we'll discuss why it is so. Now we're going to talk about tetrahedral void in FCC. Now I'm going to draw a cube and I'm going to consider this point as my origin. So I'm going to draw the axis, positive x, positive y, and positive z or z. And this atom is my origin atom. This is the atom of the origin. Now how many faces come and meet at this corner? There is one face which is the top face, there is one face which is the left face, and there is one face which is the back face. So I'm going to draw these 3 face-centered atoms, top face, back face, and left face. These are the three faces which meet at that corner. Now suppose I place my red atom at the center of this. Now let's consider this to be the origin, the corner atom to be the origin. This is my origin 0, 0, 0. Let the length of the unit cell be A. Then the coordinates of this fellow is going to be A by 2, 0. What about this guy? This is going to be A by 2, 0, A by 2, and this fellow is going to be X0, A by 2, A by 2. Now let me place the red atom at coordinates A by 4, A by 4, A by 4. Then it would be equidistant from these four, and you can calculate that by using the distance formula. It will be root 3 A by 4. The distance from all these four will be equal. Therefore, if it is big enough to touch one of these, it will be big enough to touch all the four. And that would be in the form of a tetrahedron. This is a tetrahedron. Now, since this is completely inside the unit cell, A by 4, A by 4, A by 4, and you can assume each corner to be the origin, and you'll get one unique tetrahedral void, there'll be 8 of them. The number of tetrahedral voids in an FCC unit cell will be 8, assuming each corner as origin, and it has been found that the number of tetrahedral voids in a unit cell is always twice the number of octahedral voids, or twice the rank. Now, of course, we'll later on come back to it and understand why it is so. Now what I'm going to do is, first of all, I'm going to prove that this is a tetrahedron. Octahedron is easy because the angles were 90. But here we need to understand what is the angle. So I'm going to draw these three atoms and their coordinates, and I'm going to try and figure out this angle. And I'm going to use vectors for that. So this is the blue atom, this is the corner atom 0, 0, 0. Then this is this face-centered atom A by 2, A by 2, 0. This is my red atom, which is A by 4, A by 4, A by 4. And these two are joining, and I need to find the angle between this. So let this be vector A, and let this be vector B, and let this be angle theta. So we need to find the angle theta, and I'm going to use vectors in this. Remember, this is the corner atom A by 0, 0, 0. This is the top face centered A by 2, A by 2, 0. And this is my tetrahedral void atom A by 4, A by 4, A by 4. So this is my vector A and this is my vector B. So what is vector A equal to? It will be A by 2 minus A by 4i plus A by 2 minus A by 4j plus 0 minus A by 4k. And that would make vector A as A by 4i plus A by 4j minus A by 4k. Now let's understand what is B vector. Since in the B vector and the direction is this, they are all 0, it will be minus A by 4i, minus A by 4j and minus A by 4k. So all of them would be negative. Now what is A dot B? A dot B is mod A mod B cos theta. That's how we can get the value of theta here. So A dot B is mod A into mod B into cos theta. Now what is A dot B? A dot B is, remember, I into I is 1, I into j and I into k is 0 because we talk about cos theta there. So this is going to be a minus a square by 16. This is going to be another minus a square by 16. And this is going to be plus a square by 16. So 1 plus a square by 16 and 1 minus a square by 16 will get cancelled. We'll be left with only a square by 16, negative. So A dot B is negative a square by 16. Now what is mod A? Mod A will be square root of this. That would be a by 4 square plus a by 4 square plus negative a by 4 square. That will be root of, you can add all of them, it will be 16. So it will be a square by 16 plus a square by 16 plus a square by 16. It will be 3a square by 16. That is how you get mod A. So mod A and mod B would be equal, and they would all be equal to 3a square by 16. So what is cos theta? Sorry, this is going to be mod A into mod B because it is under root of this. So this will be actually mod A and mod B would be root 3a by 4, and when you multiply these two, it will be 3a square by 16. So what is cos theta? So cos inverse of A dot B, cos inverse of A dot B upon mod A mod B is going to be theta. So this is minus a square by 16, mod A into mod B is 3a square by 16. That gives you cos inverse negative 1 by 3, and this value comes out to be 109.268. Therefore, this angle is the angle of a tetrahedron. Now, there is another way of looking at a tetrahedral void in a FCC unit cell. You can assume that the FCC unit cell is broken into 8 parts. You know that every cube can be broken into 8 parts, 4 cubes on top, 4 cubes at the bottom. And you can keep one atom at the center of every small cube, assuming that the bigger one is FCC, then these would be tetrahedral voids. And the bigger one is the green one is the FCC, and the center of every small cube is the tetrahedral void. And obviously there will be 8 cubes which make up a big cube, and there will be 8 tetrahedral voids. Now let's talk about why is it that octahedral voids is equal to rank and tetrahedral is twice the rank. This was the question that we wanted to answer. Now what I'm going to do is, I'm going to talk about octahedral first. Then I'm going to talk about tetrahedral. And I'm going to take FCC as an example. Whatever I talk about FCC would be applicable for hexagonal primitive as well. Now, how is an octahedral void formed? There are 3 atoms like a triangle and 3 atoms reverse triangle on top. And this void becomes an octahedral void. I'll just show you that in 3D. And you will notice this is an octahedron. Can you see? Square and one on top, one at the bottom. Now look at it from this point of view. Isn't this a triangle? And what is the reverse triangle at the back? Can you notice that? Or just let me pull this up and can you see? Reverse triangle. Reverse triangle on one side and this kind of a triangle on one side. So that gives you an octahedral void. So wherever you find a space like this, it's an octahedral void. Now what I'm going to do is, I'm going to draw the A layer. Then I'm going to talk about the B layer and I'm going to focus on this atom. I'm going to find out how many octahedral voids is it associated with. Now right now, it's only one B atom, B layer atom. Let me put some more. Now, look at this one. The moment I put this one, can you see this becomes an octahedral void? And this atom, don't you think it resembles this atom? It's on the left side of the triangle. Left side of the triangle. So this becomes this atom in this particular void. Let me put some more. Can you see there is one more octahedral void here? And it is this kind of a triangle now. It is on the right side of the triangle. Doesn't it resemble this one now? Okay. So there are 2 of them. And what about this one? Now in this case, the triangle is like this. And this is occupying this point of the triangle. That is, it is looking like this now. So it has occupied these 3 positions in different octahedral voids. So in 3 octahedral voids, between one layer of A and B, it has occupied these 3 positions. Now let's put the C layer on top. Remember, I'm talking about FCC. So we are going to talk about C layer on top. So be very careful in observing this. Now remember, I'm looking at this atom, this guy. Okay. So can you see this is also an octahedral void between the C layer and the A layer? Now doesn't this atom look like this atom now? Behind, top, behind, top. So it occupies this position now. Okay. Let me put some more. Now look at this guy. It is behind. Now this atom is behind bottom left. Behind bottom left. Now it looks like this atom. And now behind bottom right. This atom, this green is behind bottom right. That is this one. So in a way, you will notice that this green atom is occupying all the 6 positions of an octahedron in different octahedral voids. And therefore it can only be in 6 octahedral voids, because it has to occupy all the positions once. So each atom in FCC is associated with 6 octahedral voids. Now since in a single octahedral void, it is just one of the atom out of the 6. So each octahedral void has a contribution of 1/6 to an atom, because each void is made up of 6 atoms. So we can say that the contribution of a void to an atom is 1/6. And since that atom is already associated with 6, 6 into 1/6 is 1. That means there is one octahedral void per atom of a unit cell. And therefore, since rank itself is the number of atoms per unit cell, octahedral voids have to be equal to rank because there is one octahedral void per atom of the unit cell. So every atom will be involved in 6 octahedral voids, as it would occupy each of the 6 positions in the 6 voids. Each void will contribute 1/6 to an atom. Since an atom is a part of 6 voids, each contribution of 1/6 to it, in effect one octahedral void is associated with an atom. Since rank is the number of effective atoms in a unit cell, the number of octahedral voids is equal to the rank of the unit cell. So that way we can understand why octahedral void is equal to rank. Now let's understand why tetrahedral void is twice the rank. Now, tetrahedral voids can be formed from 3 atoms and 1 on top, or 1 at the bottom, 3 on top. Again, they could be in any form. There will be a triangle and 1 atom there. Let me show you that in 3D. This is how a tetrahedral void looks like. So 3 here, 1 at the back, 1 on top, 3 here. You can look at it whichever way you want, and the triangles can go here, can be like this, can be like this. The triangles can take any shape. It can be a straight triangle, it can be an inverted triangle, it doesn't really matter. So what I'm going to prove to you, that every atom is associated with 8 tetrahedral voids. So let's again draw the A layer. Now I'm going to draw the B layer, and again I'm going to focus on this green atom. And can you already notice that the moment I place it here, this void becomes a tetrahedral void? And can you see this resembles this atom? Isn't it? So let's call it octahedral void number 1. Now let me place one more atom here and 1 here. Now can you see this point becomes a tetrahedral void? 3 and 1 at the bottom. Now doesn't this resemble this guy? 2. So this becomes 2. Now let me put some more. Now can you see this is also tetrahedral void? 3 and 1 at the back. Now doesn't this resemble this fellow? So that's number 3. And again there's a tetrahedral void here. Can you see this resembles this guy here? So that is tetrahedral void number 4. Now I'm going to place the third layer on top. Now the moment I place this, isn't this also a tetrahedral void? Isn't this a tetrahedral void now? 3 and 1 on top. Now doesn't this resemble this guy? 5. And let me put 1 here. And this becomes 6. Why? Because the moment I put it here, isn't this also a tetrahedral void? And doesn't this resemble now this atom? Number 6. And when I put the next atom, it gives me 2 voids. One is this becomes a tetrahedral void. And doesn't this green look like this fellow? Back, right, so 7. And can you see it also becomes a tetrahedral void on its own, because these are 3 red and 1 at the green. So this is the 8th void that it is in contact with, and that is number 8. This is number 8. So can you see that this atom is associated with 8 tetrahedral voids, and therefore now the fact that it is contributing to 8, so each void will have only 1/4 contribution, because each void is made up of 4 atoms. So each void has only 1/4 for an atom, and an atom is associated with 8 of them. So 8 into 1/4 makes it 2. So per atom there are 2 tetrahedral voids, and therefore if the rank of a unit cell is x, then the number of tetrahedral voids will be 2x, twice the number of rank. So every atom will be involved in 8 tetrahedral voids. Since a tetrahedral void will be formed by 4 atoms, a tetrahedral void would contribute 1/4 to an atom. An atom is involved in 8 tetrahedral voids, with each contributing 1/4. It implies that each atom is in effect associated with 2 tetrahedral voids. And since rank is the number of effective atoms in a unit cell, the number of tetrahedral void is twice the rank of the unit cell. Now I'm going to show you octahedral and tetrahedral voids in hexagonal primitive unit cell. To make it easier to understand, what I'm going to first of all do, if you remember when we discussed the hexagonal primitive unit cell in the previous video, I first of all showed you a big unit cell, hexagon-like unit cell, and later on I said, okay, I can break it into 3 pieces, small rhombuses, and actually the rhombus one is the unit cell. Now let's consider the bigger one as the unit cell. And because it becomes easier to understand that way, and then we will make it 1/3. Because all extensive property for the smaller one would either be 3 times or 1/3, depending upon whether it is going to increase or decrease. And all intensive properties will be same. Now since rank and therefore voids are extensive properties, so whatever is the value for the bigger unit cell, for the smaller one it will be 1/3 of that. So assuming the 3D hexagonal lattice to be the unit cell, we should expect 6 octahedral voids in the hexagonal primitive and 12 tetrahedral voids. For the actual unit cell, it would be 2 and 4 respectively, and I'm talking about the smaller one. So let's have a look at that. Okay, how is an octahedral void forming? 3 on top, 3 at the bottom. So this is my layer A. Remember, we are talking about hexagonal primitive ABA. Now, this is my hexagon. We're going to find everything inside it, okay? Can you see an octahedral void here? This is between the bottom A layer and the upper B layer. Octahedral void here, 3 blue and 3 red intersecting at this point. Octahedral void number 1. Octahedral void number 2. 3 red, 3 blue. And octahedral void number 3. 3 red and 3 blue. And all these 3 voids are inside the hexagon. And therefore, when I place another layer A on top of this B, I get similar 3 voids. So that makes it 6. And that is what we were expecting. 6 octahedral voids for the bigger one, and 1/3 of that 2 for the smaller one. And we can even look for the smaller one here. Octahedral voids are here, here and here. 3 octahedral voids between layer A and B. 3 more between B and the upper A. Total is 6. Now for the smaller one, let's draw the rhombus. Now for the rhombus, as you can see, there is 1 inside and there will be 1 on top of the B and the top A layer. So that will be effectively 2, which is what we were expecting. 2 to be the value for the smaller unit cells. So that's pretty simple now. Let's look at tetrahedral void. This is going to be a little bit of a problem, but just pay attention. And how do you get a tetrahedral void? 3 and 1. And the 3 could be arranged like this and 1. So now what I'm going to do is I've already drawn my A and B layer. So I'm going to just make certain atoms disappear to show you where the tetrahedral voids are. Remember, it's 3 and 1. Look at this. 3 and 1. So this is one tetrahedral void. Let's bring back the others. Now let's make these disappear. Can you see again a tetrahedral void? 3 and 1. 2. So already 2 inside. Can you see this is also a tetrahedral void? 3 and 1. And these 3 are inside. So these are 3. And look at 4th one. 3 red on top, 1 blue at the bottom. So there are 4 tetrahedral voids. Now if we assume only 4, then on the top A layer again there will be 4. That makes it 8, whereas we expected this to be 12. Remember, the rank of the bigger unit cell was 6 and the tetrahedral expected to be 12. Well, it's not 4, it's actually 6. That's because look at the corners of the hexagon. Look at the corner of this hexagon. Isn't this also a tetrahedral void? Right at the tip of the hexagon. Isn't this also a tetrahedral void? Look at this. This yellow point. I place an atom here, this yellow point. I place an atom here, yellow point. Place an atom here. They are all tetrahedral voids. Can you see tetrahedral voids are appearing at the corner of every hexagon? Now remember, these voids are sandwiched between this B layer and the A layer. These voids are in between these two. Now this angle is 120, so only 3 unit cells will share this. Angle is 120, so only 3 unit cells can share this. So this contribution is 1, 3. Do not think that the ones on top will share this, because remember, these are sandwiched between the A and the B layer. So they can only be shared by 3 unit cells. So the contribution is 1 by 3. 1 by 3 into 6. That is what you got to see. 1 by 3 into 6 is how much? 2. 2 plus 4? 6. 6, that is between 1 A and B. Put another A, 6 more, 12. There are 4 tetrahedral voids inside the unit cell and 6 on the tip of hexagon with a contribution of 1/3. Total is 12. And for the rhombus one, obviously it will be 1/3 of this, 4. Let's see that also. This is the rhombus one. There is already one inside. Now this angle is 60, so 6 unit cells will share this. 1 by 6 into 2, 1 by 3. This is 120, 3 unit cells will share this. So 1 by 3 into 2, 2 by 3. So this is 2 by 3, this is 1 by 3, effectively it's 1. 1 plus 1, 2, and put another A layer on top, 2 more, that makes it 4, 1/3 of 12. So for the rhombus type unit cell, the total octahedral voids per unit cell is 4. So that is the end of this video where we talk about octahedral and tetrahedral voids. Please go through this video as many times as you feel like, as many times as you think is required for you to understand these things thoroughly. I hope I made certain things very clear in this video. If you have any doubts, any questions, any queries, any comments, please drop them in the comment section below. Please do subscribe to this channel in case you haven't already, because this motivates me in making more and more videos like this. And in case you like the video, please hit the like button too. This is Kalyan Kumar signing off. Have a great day and thank you for watching.